Test. Check. Check, check, check. Check, check, check. All right, let's go ahead and get started. Welcome back. Quick administrative stuff. Homework 3 is now out. It's due a week from today. 2 weeks from yesterday is the first midterm. This will be the last homework before the first midterm, and this will be the things that will appear on the midterm are the things that will appear on homeworks 0 through 3. So that'll be some of the stuff that I'm talking about today, some of the stuff I'll be talking about on Thursday. The last lecture before the midterm is canceled. University policy, if we give an evening exam, we have to release you from an equivalent amount of class time. Coincidentally, I will be in this room next Thursday at 11 o'clock to give a completely optional review session. Your TAs will also be available Friday at the usual times, coincidentally, to offer a shorter 1-hour review session. I'll have more information about the midterms as the dates get closer, in particular, where the midterms will be located, how to sign up for conflict exams, and a bunch of practice material so that you have things to play with going into the exam. Homework 2 is due today. I do find myself in a position of needing to make a couple of important clarifications. There's a problem that asks, here's a regular expression, please create an NFA using Thompson's algorithm, and then please reduce that using the incremental subset construction. What we are looking for is the output of those algorithms, full stop. Do not apply any other optimizations. We know that the DFA you're going to get is going to have additional states. Leave those states there. We know that the NFA is going to have extra epsilon transitions that you could get rid of. Don't get rid of them. In particular, I need to talk about, and I need to actually record this. I need to talk about some imprecision that was in my lecture from Thursday because I woke up at 5 in the morning and had a revelation which was wrong. And the proof that you can create an NFA that accepts the language A star, where A is a language where you already have an NFA. You really do have to take your machine for A and add in a new start state and a new accept state and new epsilon transitions, like so. You can't just have an epsilon transition at the beginning. You can't just have an epsilon transition at the end. And if you want an example to convince you, try building an NFA using the modified algorithm for this regular language and see if your NFA accepts the string 0, 0. The reason why you need those extra epsilon transitions is because given the induction hypothesis, which is that's an NFA, it has a start state and an end state, and they're distinct. If you tried to short circuit things, for example, by taking the machine for A and just adding in an epsilon transition going one way and an epsilon transition going the other, what you might end up doing is, because this is a part of a bigger Kleene closure, there might be another epsilon transition coming from far away and leading off to some far away accepting state. But then you might be able to do something like go in here, wander around in the machine for A, and come back to the accepting state, and then jump straight to the start state of machine A, and then immediately accept. And that's not an accepting path in A. It's just a path that happens to start and end at the start state of machine A. You can do similar things with the accepting state of A. So you really do need those epsilon transitions. Now, there are circumstances where those extra epsilon transitions are redundant. It's not always incorrect. In particular, if you use the quote-unquote simplified algorithm that I tried to present in class, all of the NFAs that you get for the languages in the labs and all of the NFAs that you get for the languages in the homeworks will be correct. And since we presented this buggy algorithm in class and in the labs, we're not going to take points off for it in the homework. But you do need to be aware that it's a bug, and you do need to be aware that past the current homework, we will expect you to execute the algorithm as described in the notes. For similar reasons, when you're building a DFA for the concatenation of A and B, you really do need the epsilon transition between these two machines. Otherwise, if you imagine that A is a Kleene closure and B is a Kleene closure, you can wander through A to the beginning and then through B, and because these two things are identified, you can sort of push your way backwards into A. You need to know that when you've left A, you have left A forever. And so, again, this doesn't always cause a problem, but because it sometimes causes a problem, that means it's wrong. And so you really do need to include that. Again, we're not going to count off for that in the homeworks, because in the homeworks it turns out not to matter. But beyond this homework, you really do need to put that transition in there. Yes? Yes. Okay, so this is what I mean about this doesn't always cause a problem. If there's something intermediate in here where you know you can't go back, then it's perfectly safe just to glue the two things together. So in particular, we will allow the simplification that if you have the string 001, you just write down the three transition 001, and that's fine. But because the purpose of this is to show that you can convert automatically any regular expression into an NFA, any kind of manual optimizations that you do after that is kind of missing the point. Did we lose audio for a second? It's kind of missing the point, right? Now, you can add these optimizations in, but on the other hand, you're about to turn that NFA into a DFA, and then after that, you're going to run the algorithm that minimizes the DFA, so there's no point. Okay. Yes? So when you're doing the concatenation, the final state of the start state of A becomes the start state of the new machine, and the accepting state of B becomes the accepting state of the new machine. Yes? So if you remember from the DFA rubrics, it says the way there are multiple ways that one can describe a DFA. One of them is to write down a transition table. So once you've written down the transition table, you've named all the states. The transition, the subset construction gives you that list of the states are named according to the subset of NFA states they came from. You've specified the transition function. You've specified which ones are accepting. That means you're done. Yeah. So the question is, suppose you write down the transition table correctly, and then when you're drawing the DFA, you make a mistake. This falls under the heading of the graders will grade one response. If there's a mistake in the response that they grade, they will count that as a mistake. The official solutions will have both the table and a drawing, and it'll actually further talk about how to reduce the DFAs that you get down to minimality, but that's outside the scope of the homework. You don't need both. One or the other is fine. It's a lot easier to tell that the drawing is correct, which means it's a lot easier to check after the fact that, in particular, it's a lot easier to check after the fact that the result of the construction actually accepts the language that you started with if you have a drawing than if you're just having a table. So even if you don't submit the drawing, I strongly recommend drawing the DFA and doing a sanity check to make sure it actually accepts the language that you started with to make sure your answer is correct. Okay. So over the last lecture, we had this sort of round of reductions where I can take a regular expression, and by way of Thompson's algorithm, I can get an NFA that happens to use epsilon transitions. And then, if I want, I can get rid of the epsilon transitions. On the other hand, I can't spell. Once I have an NFA either with or without epsilon transitions, by doing this subset construction, either directly or through this incremental form, I can get to a DFA, and then later, if I want to, using an algorithm that's described in the notes, but I'm not going to talk about in class, I can reduce that DFA to a minimum number of states. Now, there's one piece left that I didn't have a chance to talk about at all, which is closing the loop. How do I go from a DFA back to a regular expression? If I'm given, some machine that accepts the language, the claim is that that language is regular, and the definition of regular is there's a regular language that describes that machine. And so the first thing I want to do is finish this proof of equivalence by sketching, and I'm going to do this at a very high level. I'm not going to run through a complete example of the algorithm because actually I think getting the idea across is more important than actually watching the algorithm completely execute to completion. But starting with a DFA, how to turn it into a regular expression. And the way I'm going to do this is I'm going to consider, I'm actually going to start with not a DFA, but with an NFA. So I'm gonna, just because all DFAs are NFAs, that's no problem. But I'm going to start by making my NFAs more and more general, and to argue that by increasing the generality of my NFAs, I'm not changing the sets of languages that they can accept. I'm just making essentially a change in notation. Okay. So we've already seen that you can take NFAs where every transition is labeled with a character from your alphabet, and you can augment them by adding transitions that are labeled with the empty string, the so-called Epsilon transitions. These are sometimes called Epsilon NFAs. I just think of them as NFAs. We saw by chasing down the epsilon reach of every state that you can add in new transitions to get rid of these epsilon transitions if you want to. So I can further extend this to an intermediate form that I call a string NFA. So I can give an example here. So this is a string NFA. The semantics of the drawing are that, remember, with an epsilon NFA, if I want to know whether I can walk across an arrow from one state to another, I look at the label, and if it's empty, I can walk across that transition and not consume anything of the input. If it's a single character, I can only traverse that arrow if it matches the first remaining character of the input. Similarly, if I have an arrow that's labeled 111, I'm allowed to traverse that arrow if and only if the next three characters of the input are 111. And if I walk across the input, then I consume those three characters. And now this becomes a much more general pattern. If the label of an arrow leaving your current state matches a prefix of the remaining input, you're allowed, but not required, to consume that prefix and move to the other state. Okay. So if I'm staring at this this particular NFA, for example, and I see 10101111. One possibility is I could stay put, then move to the top, then move to the bottom, then move to the top, then move to the accepting state. So I see this 1, and I use it to traverse that loop on the left. I see this 0, 1, I use it to traverse the arrow up to the top. This 0 takes me to the bottom, the empty string takes me to the top, and the 3 1s take me to the accepting state. Now, I could have started out by taking this first 1, 0 and going to the bottom, and then epsilon to the top, but then I'd kind of be stuck. There's no, once I've reached the bottom, if my next character is a 1, there's actually nothing I can do. So that particular execution thread gets killed. Okay? And so a string NFA accepts a string if and only if it's possible to divide up the string into substrings so that these substrings are the labels of some walk from the starting state to some accepting state. Right? This is just what we normally do with epsilon transitions, only with epsilon transitions, every label is either a string of length 0 or a string of length 1. Now I'm just allowing strings of arbitrary length. Now, this is clearly not really much of an extension because I can just expand any non-empty string into its individual characters, subdivide that corresponding edge in the transition graph by introducing new states in the middle, and it's exactly the same. Okay? So, is everybody clear when I talk about a string NFA, what I mean. I should point out that some people use this as the definition of an NFA. It's not as common as the other definition, but it's a perfectly reasonable definition. It just requires a little bit more work to turn things into DFAs if you do that. Okay. Now, the next thing that I want to do is to observe that if I had two transitions going from one state to another like this, I have an option of if the next three characters of the input are 1, 0, 1, I can make this transition. Or if the next three characters in the alphabet in the input are 0, 1, 0, then I can make this transition. Just as a matter of notational convenience, I could write that as just by putting a plus in there. Okay, just fine. Okay. This is just a nice way of actually combining, I suppose, one could call this a finite, now I'm labeling, in effect, the transitions of my NFA with arbitrary finite sets of strings. Anyone want to guess what the next and actually last step in this set of generalizations is going to be? Yeah. Yeah. I could actually label a single edge in my NFA with not just a regular expression involving strings and pluses, but an arbitrary regular expression. And now the rules are what you would expect. An expression NFA accepts a string if it's possible to divide the string up into substrings and find a walk from the start state to an accepting state where the corresponding substrings match the corresponding regular expressions. So this is actually, it's a fairly natural idea, but the surprising thing was the earliest reference I can find to actually thinking of this as a machine as opposed to just some abstract formalism is in a paper by one of my colleagues, David Wood, and his student, whose first name I forget, named Han, in 2005, which I realize probably seems like ancient history to you guys, but considering that it was 20 years after I first saw this material, it still strikes me as somewhat incredible. Right, so the idea is that I could have a machine that's labeled with an arbitrary, where a single transition is labeled with an arbitrary regular expression. And again, I'm allowed to transition from this state to that one if and only if some prefix of the input matches that regular expression. And then when I walk across the transition, that prefix gets consumed. Now, one distinction here is that there may be several different prefixes of the input that match this regular expression, and I get to decide non-deterministically which one to choose. So the same rules apply as when I get to decide which state to transition to. I have different ways of executing the same transition. If you like, a little birdie lands on your shoulder and tells you the right way to do it. If you prefer that I take all possible ways of matching this regular expression to some prefix of the input, and I spawn off a different execution thread for each one. Now, how do I know that I haven't, this doesn't, I can turn this back into a standard NFA? How would I turn this transition back into something that looks like a normal NFA. Yes? Yes! That's exactly right. So I could apply Thompson's algorithm, and I would get, what would I get? Okay, so there's this, and then there's a 1, and then this is a 0, and then an epsilon transition going to thing for 1 star, then this, and then an epsilon transition going to 0, and then that goes to this. Right. So I can apply Thompson's algorithm and just say, let's pretend that this transition is in fact the entire NFA, and apply Thompson's algorithm, which always gives us an NFA that has 1 start state and 1 accepting state, and just glue this in place of this single arrow. The semantics don't change. The new NFA accepts exactly the same language as the original string NFA. The branches and so on that I've added over here by running Thompson's algorithm encode all of the non-deterministic choices about which prefixes which prefix I'm going to pick. Whereas in the expression NFA, there's a non-deterministic choice for how to consume the input. That non-deterministic choice goes away here, except whether to consume the empty string or not. But then there are lots more non-deterministic choices of transitions going on inside. The punchline is that Thompson's algorithm allows me to think of these regular expression labels on NFAs, and it's just shorthand. I can mechanically transform that into a regular standard textbook NFA. Okay? So now I really want to go from this to a regular expression. And here's the way that I'm going to do it. Notice when I expanded a regular expression NFA into a standard NFA, the labels got shorter, but the number of states blew up. Now I'm going to try to reverse that by saying, okay, every time I move down the chain, my labels got more expressive, but the number of states went down, potentially. So what I'm going to tell you is how to remove 1 state from an expression DFA, or expression NFA, to get an equivalent expression NFA. If I can get rid of 1 state, at that point I can apply induction and get rid of all of the states except the start and the accept state. So the idea is the following. I would really like to get rid of this state, say. Now, the problem is, let's look at these other 2 states. Let's call the one on the left. Let's say this is P and this is R, and I have this intermediate state Q that I really want to get rid of. I need to get rid of it in a way that doesn't change the language that the expression automaton can accept. Now, there might already, in fact, be a transition from P to R, say labeled like this. But if I just delete Q and all the incoming and outgoing transitions, I'm potentially deleting a subset of strings that can get me from P to R. So I need to change the label of the direct transition from P to R to include those strings. So how would you describe, given just this picture, A, B, C, and D are regular expressions, how would you describe the set of all strings that can take you from state P to state R? P plus A B star C. Okay, now if I put that in, this path that goes from P up to Q and maybe goes around, sits at Q for a while and then goes to R, is redundant. Because every word that matches that path, that walk from P to Q to Q to Q to Q to Q some number of times and then to R, now matches this regular expression, A, B star C, which is now part of the transition from P to R. So whatever prefix of the input matched that complicated loopy path, now in the modified expression machine also just matches the single transition. Okay, so I can imagine now doing this for, if I want to get rid of state Q, I apply the transformation on the screen for every pair of states P and R. Okay, for all states P, for all states R, modify the transition from P to R according to this template. At that point, every walk through the machine, through this transition graph that passes through state Q is equivalent to a walk through the machine that does not pass through state Q. And so I can just delete state Q. All right? We will potentially see this picture again when we're looking at shortest path algorithms. This is almost exactly the same picture that one can apply to, it's sort of the Floyd-Warshall all-pair shortest path algorithm, if you've ever seen that before. If you haven't, a month from now you'll go, oh, yeah, I see. That thing he did with the expression automata, it's the same thing. So as I said, I'm not sure that I need to say anything else. I mean, we could walk through an example, or you can look in the notes to walk through an example. But the basic idea is I'm going to pick a state that isn't the start state and isn't an accepting state. For every other pair of states, I'll modify the expression labeling the transition from one to the other according to this template, and that will allow me to get rid of that intermediate state. I repeatedly get rid of states until the only states left are the start state and the accepting state. When that happens, what I'm left with is a start state and an accepting state with a regular expression on it. And now this accepts precisely the language described by that regular expression. And so we've retrieved the regular expression from the NFA. Now, in order to make this work, there are a couple technical conditions. I need to start with an NFA with the property that there are no incoming transitions to the start state and there are no outgoing transitions from the single accept state. But those are easy conditions to satisfy with Epsilon transitions. In particular, you get them out of the Thompson's algorithm immediately. Huh? So that ends the proof that NFAs and DFAs and regular expressions are equivalent. Now, I do want to point out something about the proof, which is you'll notice when I apply this algorithm to an NFA that has n states, every time I get rid of one state, very roughly, the labels of every other edge in the transition graph grow by a factor of 4. Which means if I start with an NFA that has n states, I'm going to end with a regular expression that has length roughly 4 to the n. Similarly, with the subset construction, if I start with an NFA that has n states, there are 2 to the n subsets of NFA states, and therefore there are 2 to the n DFA states. So the subset construction can give me a DFA that's exponentially larger than the NFA that I started with. And sometimes all of those states are necessary. Similarly, if I'm given a DFA, turning it into a regular expression can blow it up exponentially. If I start with a regular expression, turning it into a DFA can blow it up exponentially. The most compact representation is actually an NFA. And so if you're actually using these to do really complicated pattern matching tasks, probably you don't want regular expressions and probably you don't want DFAs. You really want an NFA. That makes deciding acceptance a little bit more complicated, but there's still fast algorithms to do that. Unlike DFAs, where there's an efficient algorithm to compute a minimum one, and the minimum DFA is unique, minimizing regular expressions is hard. There isn't necessarily a unique minimum length, minimum size regular expression for a given language. Deciding whether a given regular expression can be further minimized is NP hard. It's ugly, it's nasty, it's horrible, it's no good, very bad. So really, regular expressions are useful only because we can type them. They're not particularly expressive and they're hard to optimize compared to the machines that they actually turn into in the background. Yeah. So if I say, regular expression of length n, if I turn it into an NFA using Thompson's algorithm, the size is going to be order n. If I turn it into a DFA, it might have size exponential. If I start with a DFA that has n states, of course I can turn it into an NFA that has n states by just saying, look, it's an NFA. But then if I try to turn that into a regular expression, that could have length 4 to the n in the worst case. So this one in the middle is actually the most compact. Going to either of the other two representations could really screw you up. Yeah. So you take epsilon transitions from those multiple accept states to a common single accept state, and then you collapse them, or you just say multiple accept states, okay, it's R1 plus R2 plus R3 plus R4. Yeah. Sure. So one example is, let's say I'm working over an alphabet of size k. I want to accept strings where some character of the alphabet appears more than once. You actually have to keep track of the subset of symbols in the alphabet that you've seen. But it turns out with an NFA, you can actually do that in order k states. I'm sorry? Yeah, I mean, it's not that every NFA turns into a DFA with exponentially many states, but this just is, the worst case is 2 to the n, and there are examples where it's omega 2 to the n. It's always O 2 to the n. So this is the worst case. Okay. All right, so the last thing I want to talk about with regular languages is more general ways of transforming them. So several instances in the last couple of weeks, we've seen descriptions of how to take a DFA or an NFA and change it into some other DFA or NFA. So for example, we saw how to take DFAs that accept two languages, L and L prime, and combine them into a DFA that accepts the language L intersect L prime. We saw an algorithm that takes an NFA with epsilon transitions as an input and produces an NFA without epsilon transitions as an output. We saw an algorithm that takes an NFA as input and returns an equivalent DFA as output. So I want to push on this a little bit more by showing that essentially you can answer questions of the following form. Given any regular language L, prove that some function of that language is also regular. Okay, so an easy example is prove that the complement of a regular language is regular. And the way that that proof works is, okay, so example, f of L equals sigma star minus L. When I say given the regular language L, what I'll actually say is given any DFA, let's call it M, which consists of a set of states, a start state, a set of accepting states, and a transition function that accepts L, we build a DFA M bar, which I'll formalize as Q bar, S bar, A bar, and delta bar that accepts L bar, which is the complement of L, as follows. And the intuition is that I'll use the same states, I'll use the same accept state, the same start state and the same transition function, but I'll use the opposite states as accepting from the DFA that I started with. So if I wanted to write this down formally, I would say, Q bar equals Q, S bar equals S, delta bar equals delta. I don't need to specify it further than that. And A bar equals Q minus A. Okay, so swap the accepting and rejecting states of M. Okay. So this is a simple example of the kind of argument that I want to try to do a few examples of. You'll do a few more examples of these in lab. You'll do a couple more examples of this in the homework. You'll do one example or two of this on the exam. And what I'm really doing here is getting you used to the idea, because it's going to show up again later in the semester. You're used to thinking of these machines as code, but they are also data. A DFA is a data structure. A regular expression tree is a data structure. It can be represented by a finite sequence of bits in memory, and therefore it can be fed to an algorithm as input. And then that algorithm can understand that data structure, manipulate it, and turn it into a different instance of the same or a similar data structure that means something else. So this is an algorithm. It's a very simple one. It takes an arbitrary DFA. I know nothing about the DFA at all, and mechanically transforms it into another DFA where I can say something about the languages that the two DFAs accept. In this case, they're complements of each other. This is the kind of argument that I want to play with. The thing to keep in mind over and over again is you know nothing about the input language L except that it's regular. So we define now the reverse of L. This is the set of the reverses of all strings in L. Okay? So without worrying about formality yet, intuitively, how would you prove that if a language L is regular, then its reversal is regular? I'll give you an opportunity to apply the standard answer. How would you prove mumble, 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 mumble? Okay, induction on what? The language is probably infinite. That won't work. Good. Okay, L is regular, and therefore it can be represented as a regular expression. If I'm trying to make an inductive argument about a regular language, one way to do that is to assume I have a regular expression for L, and then argue inductively about transforming that, that regular expression for L into a regular expression for the reverse of L. Now, I'm not going to write down all the boilerplates, but I'll just write down a couple of examples. Reversing the empty set gives me the empty set. Reversing a, well, this sounds a little trivial here. The one on the left means W as a regular expression representing the input string, and I'm reversing the regular expression. The one on the right means the reversal of W as a single string, which I'm using as a regular expression. If you really want, you can say, okay, I'm going to write strings in red and regular expressions in blue. All right, so the regular expression that indicates the singleton language W reversed is the same as the regular expression involving the single string W reversed. Okay. A plus B reversed is A reversed plus B reversed. A star reversed is the same as A reversed star. And then finally, A dot B reversed is what? B reverse dot A reverse. Okay, so I can take an arbitrary regular expression, parsed out into an expression tree, and then mechanically modify the regular expression until I get a regular expression that corresponds to the reverse language. This requires some further inductive definition chasing to prove that it's correct. This is great when it works, but it really only works for fairly simple functions. So in particular, you can't start with the regular expression if what you want to do is prove something about complement. There really is no easy way to go from a regular expression to the complementary regular expression. I know it exists because I can turn the regular expression into a DFA and then reverse the states and then turn that back into a regular expression. But that conversion may cause an exponential blow up and blah, blah, blah. So the important thing here is to always start with the right representation. And more often than not, the best representation to start with is actually a DFA. So let's start with a DFA and try to do the same thing. Okay. So let's suppose M is a DFA that accepts my regular language L. Without trying to worry about formalism just yet, intuitively, how would you turn this into something that accepts the reversal of L? Yeah. Okay. Ah, good. So that's the key point. What you'd like to do is walk through the DFA backwards, starting at the accepting states and ending at the start state. So you just turn all the accept states into start states, turn the start state into an accepting state, and reverse all the arrows. Crap, I can't do that because then I have multiple starting states. Oh wait, oh God, even worse. Then I might have like two arrows with the same label leaving a state, because I could, in a DFA, I can have two labels, arrows labeled 0 going into the same state. Now I've got two labels, arrows labeled 0 going out of the same state. It's not a DFA anymore. What is it? It's an NFA. So I'm going to build an NFA with epsilons and typically I'll call the, sometimes just to drive this home, I'll sometimes refer to the NFA as N, but I'm still gonna, actually let me call it M reverse. I'll put this little superscript R here to distinguish between the states and so on of the original machine and the states and so on of the new machine. Okay, so I need to tell you what the states are, what the starting state is, what the accepting state is, and what the transition function is. Now, the intuition is I want to exchange which states are starting and which states are accepting. And one of those actually works pretty well. I'll just say my set of accepting states is a singleton set containing just the original start state. Okay. Now, I'd like to start at all of the accepting states. My definition of NFAs doesn't allow me to do that. So I'm going to create a new state. I'm going to add that to my set of states, like so. And then I'm going to define the epsilon transitions out of that new accept state to be all of my old accepting states. Okay, so I added a new state SR. There it is. That's, in fact, the only new state. And then I have epsilon transitions going backwards from the new start state to all of my old accepting states. And now I want all of the other transitions to be driven backwards. So for any state Q and any symbol A, I want this to be the set of all states P, such that the original transition function would take P to Q on that input symbol A. And so this is essentially just writing the arrows backwards. Now, I'm not done because the transition function isn't completely specified yet. What am I missing? What have I not written down? What is delta reverse of S reverse, comma, 0? Sorry? I'm sorry. Yeah, this SR is just the new start state. What if I get a 0, what should I do? I should blow up. Right? I mean, again, here's the intuition. I have my original machine, looks like this. This is my machine M. And now I've added this new start state SR, and I have epsilon transitions going like this. And I'm going to push all my other states backwards. This is my new accepting state. All these things go backwards. If I'm in this new start state, its only purpose is for me to non-deterministically choose one of the original accepting states. That's the only reason for its existence. If I stand at that state, if I refuse to use that state for the purpose for which it was designed, and I read a 0, I should destroy the universe. Okay, so this returns the empty set. The set of states I can get to from state S reverse using transition on symbol A directly is nothing. You can't do that. And similarly, because my original DFA didn't have any epsilon transitions in it, My output NFA also doesn't have any epsilon transitions in it, except the ones that I used, that I introduced myself to choose the real start state. So I have to write these things down in order to have a complete description of an NFA. I have to describe the transition function in totality, which means for any first argument and any second argument, I have to tell you the result. The first argument is either SR or one of the original states, and the second argument is either epsilon or one of the input symbols. Yes? Okay. If you say out loud in your solutions, all unspecified transitions are go to the empty set, then I know it's the default. If you don't write that down, I cannot distinguish between you meant it to be the default and you didn't realize you needed to write it down. And so I can't give you credit. I will point out that writing this down, the stuff I've written down in red, requires you to move the pen less than writing down all missing transitions go to the empty set. So just write it down. Okay. Similarly, when you're writing DFAs, this showed up in the official homework solutions. Sometimes you have a DFA that has a non-accepting state that you can never get out of, something called a dump state or a trash state. And if you say all missing transitions go to a dump state, and then don't draw the dump state in, then we know the dump state is there. If you don't say that, but you leave out the transitions, we don't know what the missing transitions are supposed to mean, and so we think, oh, this is an NFA instead of a DFA, or you just forgot. Yeah? In an NFA, there's no point. In an NFA, this is not a problem at all. But in a DFA, you have to specify an outgoing transition from every state with every input symbol. Right? Just like you do here. I mean, I have to specify this somehow. And I'm specifying it to be the empty set. Okay? So again, this is actually the most common version, the pattern of this. I start with a DFA, and the reason I start with a DFA is because a DFA has the most restrictions on it. It leaves me the least amount of freedom in the input that's still arbitrarily expressive. On the other hand, I produce an NFA with epsilon expressions because that allows me the most freedom to design the output. Now, I could actually have started with an input NFA, and it would not have been any more complicated. I think, you know, I'd have to change this into Q belongs to this set instead of whatever in here. But going into the problem, I don't know that. So my recommendation in general is start with a DFA and aim for an NFA with epsilon transitions if you need them. Okay. Good. So let me do a somewhat more complicated example. Okay. So I want you to spend a little bit of time wrapping your head around the definition here. Yes? So you need to give some indication of what you're doing. So you don't need to write down a formal proof, but you do need to write down an English explanation, which in this case is reverse all the arrows, right? This is the intuition of what you're trying to do. So you need to give us an explanation of what you're doing. But it's not going to be a formal proof. So a formal proof here would require a lot of inductive definition chasing. You can sort of encapsulate it by saying if you take any walk in the state transition graph of M, Its reversal is a walk in the state transition graph of M reverse. And so strings, M acts on strings in one way and acts on the reversals of those strings in exactly the opposite way. And so I've built the right start states and the right accepting states for the language to work out. Right? That's the high-level view of the proof. Actually turning that into something formal is going to be a bit too long and tedious certainly to ask you on an exam, but even to ask on the homework. So what I want is sort of a convincing high-level view of what you're trying to attempt, so that we go, oh, right, I see. This is the part where he's reversing the arrows, and here you're really choosing where the reverse, when you're running the machine backwards, where you should end. And here you're saying, yeah, you have to start at the right place, and yeah, okay, you've filled in all the details, so you know what you're doing. Good. Yeah. There is no trash state in this NFA. The empty set is the set containing no states. Right? The transition function of an NFA always returns a set. Always returns a set. When there's nothing to put in that set is empty. No, it's not the case that if you don't specify a state that somehow magically I know what it is. In the drawing, if there is no arrow leaving the state labeled 1, the transition function is formally defined as delta of q comma 1 equals the empty set. If there's a transition function leaving state q for states r, s, and t, then delta of q comma 1 is the set containing r, s, and t. That's correct. Even if it's not on the graph, you have to write it out. Keep in mind that graph is just a cartoon projecting your intuition onto the page. You're not given a graph. You're formally given an unknown DFA with some unknown structure. There is no graph in this case to point at and go, look, there's no arrow. Yes, in the back. Yeah. Okay, so close, but not quite. So the question is, we just built an NFA for the reversal of a language, and so now we know there is a DFA for the reversal of the language. So can't I just take, you know, essentially what you're saying is this should be the same as L dot L reverse. Right, concatenate L and concatenate L reverse. But that's not actually true. And it's not true for two different reasons. One is that that language L dot L reverse, I can choose any string I want out of L, and I can choose any string I want out of L reverse, and they don't have to have any relationship to each other at all. Whereas in the definition of the language on the left, it's not WX reverse, it's WW reverse. It's the same string forward and backward. Okay? The other reason it's not right is I'm not actually accepting the palindrome. I'm accepting the first half of palindromes in L. Right? So what I'm saying, for example, is if my language L contains a palindrome of length 16, your machine should accept the first 8 characters of that palindrome. Right? So, except line if and only if L contains I, L, L, I, N, I, N, I, L, L, I. Okay? All right. So I'm gonna start the way I always start. I'm gonna go, okay, this is weird, but okay, fine. I'm gonna start by saying Given a DFA M with some states, and so start state and accepting state and transitions, that accepts L, I'm going to build an NFA. Probably it's going to have epsilon transitions because that just seems to happen. I'll call that M prime, because that seems generic enough to be different, as follows. But before I get to the formalism, I need to have a plan of attack. So intuitively, I want to imagine that I have the DFA sitting in front of me on the table, and somebody is going to yell out the characters of the string one at a time. The string on the left, the line I, not the string on the right. And I want to somehow figure out what the DFA would do if I had been given the string on the right. So I can say, well, I know what the DFA is going to do on the first half, because as you yell characters at me, I can move my finger around on the graph, following the arrows going forward. But I also know what the thing is going to do at the other end, because essentially I can start with my right hand on an accepting state, and whenever you yell at a character, I move my finger backwards along some arrow. And so I start at the start state and move forward, and I start at the end state and move backwards simultaneously. So you'll I, L, L, I, N, I. And as long as they meet in the middle, that means I could have read Illini to get to here, and Inayla to get to there. Okay? So I'm going to simultaneously run the machine forward and backward and try to get the paths that are being traced out in those two machines to meet in the middle. Okay? Run both M and MR in parallel. Try to meet in the middle. Well, hang on. Maybe this is not such a good idea, because when I say try to meet in the middle, I wanted to end at exactly the same state. This is reasonable intuition, and if I remember that the way that I built the NFA for reversing M, I kept exactly the same states. I can just say, okay, I'm actually going to use this construction for the reversal. If I don't, then I kind of have to rebuild that from scratch, because I need to know what it means for the machine M and the machine MR to be in the quote-unquote same state. Okay. But, okay, that's one way, but how do I run two machines in parallel? Yeah. Exactly. The state of the machine is, where is my left finger and where is my right finger? I'm the machine. This is my state. It's described by saying, where is my left finger? That's the state in my forward machine. And where is my right finger? That's my state in the backward machine. Okay? So my new machine is going to be defined as follows. I have two copies of the machine, one that runs forward and one that runs backwards. The backwards machine needs a new start state, just like it did in the previous exercise, because otherwise I don't have any place to start. The new starting state is going to be the forward machine is going to start in the start state of M, and the backward machine is going to start in this brand new start state that I've defined for the reversed machine. Now, the set of accepting states, I'm going to accept if the forward machine leads to a state and the backward machine leads to the same state on the same input string. So the accepting states here are going to be all pairs where the two components are the same. Both machines are in the same state at the same time. Now, this ultimately is a product construction, and the transition function that I'm going to write down is exactly what you would write down for the product construction. You can apply, we did the product construction for two DFAs. Here, I'm effectively describing the product of a DFA and an NFA. You can define the product construction of two NFAs similarly. This is mostly, at this point, an exercise in fighting the notation demons more than it is an exercise in figuring out what you want to do. So the first thing that I need to do is deal with the start state, which is I want to start by saying my right finger, the one that's going in reverse, has to start at this new extreme right start state, and it has to back up to one of the accepting states of my original machine M. My left finger should not move when this happens. And this is, in fact, the only purpose of this substate S sub r. So this is going to go to all states S comma Q, where Q is an accepting state of the new machine, of the old original machine M. Okay, so this says I know where the left finger should start. I don't know where the right finger should start, so I'll set up an artificial place for it to start, and then epsilon transition to all of the possibilities where it could. Every other epsilon transition will be 0. So delta of Q R epsilon equals epsilon is the empty set for all other QR in Q prime. Okay, this is the only epsilon transition. Then I have to decide what to do if I'm sitting in the middle of the machine. My left finger is at Q and my right finger is at R, and I read the symbol A. Well, so I'm gonna, because I'm building an NFA, I need to return a set. So I need all possible things that can happen to my left finger, Q, all possible things that can happen to my right finger, R, and glue them together into pairs. So what can I do with my left finger? What's the first half of every state I can get to along this transition? Remember, my left finger is just simulating the machine M. Yeah, in the back. Delta of Q comma A. Right. No options. The forward machine is a DFA, the output, the following state. This component is completely determined by the state and the symbol that I'm reading. But my right finger has several options. So I'm going to write this in the same language that I wrote before. My right finger can back up to any state P, provided moving forward along the arrow, leaving P labeled A, gets me back to where my right finger just was. Okay, so this is, the first half of the pair is saying the left finger moves forward along the transitions. The other part says the right finger is moving backward along the transitions. Right? Again, this is just a product construction of what we did with the original machine and the reverse machine that we described earlier. And then I also need to S reverse comma A equals the empty set for all Q, because I need to specify everything that my transition function could possibly do. Okay? So my left finger moves forward, my right finger moves backwards. I need to play some games with epsilons in order for the right finger moving backwards to make sense with my definitions. So I need to establish a place for it to start, and then a way of choosing where I really want it to start. That's the only purpose of SR. Then whenever I read a symbol, the left finger moves forward according to the original transition function. The right finger moves backwards according to the original transition function, but there's more than one way to do that, so I have to write it in this set builder notation. If the two fingers meet in the middle, that means there's a path from the start state to this middle state that's labeled with W, and there's a path from some accepting state back to this state that's labeled with W, which means going forward from this state to an accept state, it's labeled with W reverse. And that means there's a path from the start to an accepting state labeled W reverse. Okay. These things, it's really amazing, amazingly convoluted things that you can do with these kinds of constructions. There are a couple of examples in the homework. As I said, there are a couple of examples in the labs. There are more worked out examples in the lab solutions. There are more worked out examples in the homework solutions, which you'll see next week. This is the hardest thing that you will do before the midterm exam. So please, if you have questions, ask us in office hours, ask us in Piazza, go to the labs, etc. All right. Thank you. See you Thursday.